Good day to everyone. Today, let's discuss how to design a solar off-grid power system for homes, and also we'll see how this system operates. First, let's see what components are needed for the system, and then we can decide the capacities of the equipment to operate the system smoothly and efficiently. Let's start from the solar panel, and these are also called PV panels. PV stands for photovoltaic, which means electricity generation using light. There are two basic types of panels, one called polycrystalline and the other one being monocrystalline. Both do the same work, transforming light into electricity, but cells on monocrystalline panels are made out of a single crystal of silicon, while cells on a polycrystalline panel are made using different crystals of silicon blended together. Efficiency of monocrystalline solar panel ranges from 15 to 20%, while polycrystalline panels are a little behind with 13 to 15% efficiency. Efficiency of the panel, of course, is the percentage of light power transformed into electricity power. When sunlight on the panel is low, voltage produced by the panel also decreases, resulting in a reduction of power and current drawn onto the system. Solar charge controller is used to monitor these ups and downs from the solar panels and to smoothen the current supplied to the batteries for charging. Charge controllers are of two types. MPPT charge controllers use maximum power point tracking system to control its output current to the battery. It will identify the current at the point where the maximum power is produced by the panel, relevant to its voltage, and will deliver this current to the battery for charging. Other type is called PWM charge controller. To regulate the charging current to the battery, voltage is adjusted using pulse width modulation here, relevant to the power produced by the panel. Since lot of on-off pulses are being used here for voltage regulation, there will be some reduction of power-based efficiency drawn from the solar panel. MPPT controllers are more efficient here, providing over 90% of maximum power available on the panels to the battery pack as charging current. Next, we need a battery pack to store electrical energy converted by solar panels. Vehicle batteries also can be considered here, but more efficient deep cycle batteries with around 100 to 150 ampere-hour capacity are more suitable. These are specially made for solar systems and can deliver uniform power continuously until it is discharged to a minimum level of 20%. Next, we need an inverter for this system, and it will transform DC power stored in the battery pack to AC power needed for electrical equipment. In general, inverters are of two types and differ according to the smoothness of the sine wave they produce. Pure sine wave inverters produce a smooth AC sine wave, very similar to what we get from the grid. The other type is called modified sine wave inverter. Sine wave produced by this inverter is on the square side and modified to get a little closer to the pure sine wave. Still, it is more like a path with square steps compared to the near-perfect sine wave on the pure sine wave inverter. If you use electronic equipment mostly during a power cut, better to go with a pure sine wave inverter. For using fans, bulbs and drills-like things, modified sine wave inverter is more economical. Let's see how to connect a solar power system now. First of all, make sure solar panels are correctly earthed. Then, panel is to be connected correctly to the positive and negative terminals marked for solar panel on the charge controller. If you use two batteries, make sure to connect those in parallel to keep the same voltage value as on a single battery. If the battery label shows 12 volts and 150 ampere hours, two similar batteries connected in parallel will have same 12 voltage, but double the total capacity, making it a 300 ampere hour battery pack. If those are connected in series, voltage will be doubled to 24 volts, and capacity also will be doubled, making it a 300 ampere hour battery pack. Now, two batteries need to be connected onto the marked positions on the charge controller. you will see that a direct 12-volt outlet is available in almost all the charge controllers, and a direct 12-volt load can be used connected onto it, even without having an inverter. Then the battery pack needs to be connected to the positive and negative terminals, marked on input side of the inverter. On the output side of the inverter, you will find the AC plug sockets and the power on-off switch. Equipment required to be operated during a power cut should be connected onto the plug sockets on this side. Total power of the equipment to be used is to be decided according to the watt power rating on the inverter. If the sun is shining like this, allowing enough sunlight onto the solar panel, battery will be charged with the current, controlled by charge controller. Also, we can use our electrical equipment through the inverter, and the power required for this is being supplied by the battery pack. When a cloud interferes and covers the sunlight like this, battery charging will be stopped, but the charged battery will supply power to the inverter continuously to operate the required equipment without any interruption. When the cloud moves away, sunlight is back, and the battery charging will be started again. Now let's see what the average requirement of electricity is during a 2 to 5 hour power cut. Here I included LED bulbs, fans and a TV only for calculation purposes. Air conditioners and refrigerators are not considered here, but you can change these things, or add more equipment according to your requirement. Total power consumption here is 350 watts. Let's select an inverter for this requirement now. Since we considered minimum power requirement only, added 40% more for any additional equipment to be used, and the rounded up figure is 500 watts. Since power factor comes into the picture here, we need to divide the output power of 500 watts by assumed power factor value of 0.8 to get the apparent power of 625 volt amperes. To understand more on apparent power, active power and reactive power, please watch my video titled Power Factor and Power Triangle. In general, inverter efficiency is around 90%. That means you need to supply 695 volt amperes as input power to the inverter. To draw out 625 volt amperes, that is 500 watts as output power, we can select 800 volt ampere inverter with 28% of extra power, or 1000 volt ampere inverter with 60% of extra power. It's always better to keep an additional allowance when choosing an inverter to make sure smooth operation of it without any overheating. It will not affect the battery selection since we use actual power input for battery selection calculations. We have selected a 1000 volt ampere inverter here, and the actual power input needed for it is 695 volt amperes. Divide this 695 value by battery voltage of 12 volts to find out the current flow on the cable which connects the battery to the inverter. You get 57.9 amperes here, and is the maximum current on this cable when all of your AC equipment are working on full load. By dividing 625 value by 230 volts, you get 2.7 amperes on the output side. On a battery, its capacity is given by the ampere-hour value. 150 ampere-hour battery can deliver 150 amperes continuously for a period of 1 hour. If we need to draw 15 amperes, this battery can deliver it continuously for 10 hours. Further, divide the battery capacity of 150 ampere-hours by 58 amperes to get the battery backup time. You get 2.6 hours backup time for 150 ampere-hour battery. For a 300 ampere-hour battery pack, backup time is 5.2 hours when you draw a current of 58 amperes continuously. Surely, you will not use all of your equipment continuously during a power cut. Even if you do that, 2 batteries of 150 ampere-hours each are enough for this solar power system, having more than 5 hours of battery backup time. When maximum power of 500 watts being used, cable connecting the battery to the inverter carries 58 amperes. Always make sure the correct size wires are being used here to avoid unnecessary hazards. Normally, inverters up to 1500 watts power need to use 4 WG size cables, having 5.18 millimeters diameter. 2000 watt inverters need to use 1/0 WG size cables, having 8.26 millimeters diameter. Likewise, 3000 watt inverters need to use 4/0 WG size cables, having 11.68 millimeters diameter. In general, solar panel sizes need to be decided according to the battery charging capacity. Normal charging current for a 150 ampere-hour battery is 10% of its capacity and is 15 amperes. Maximum charging current for this same battery is 30% of its capacity and is 45 amperes. Charging time for a backup battery pack can be found out by dividing its capacity by the charging current. When 300 ampere-hour battery pack is being charged with its maximum charging current of 45 amperes, it will be fully charged in 6.6 hours. To find out total solar panel power needed for this system, multiply battery voltage of 12 volts by maximum charging current of 45 amperes. We get 540 as the answer, and the total panel power should be 540 watts, or more than that. So we can use two panels of 300 watts each connected in series, making the total panel power of 600 watts. Maximum power generation of a solar panel is given as Pmax on the label, and the open circuit voltage between two terminals are given as VOC. Generally for solar panels, maximum sunlight is available for 4 to 5 hours, during 10 a.m. to 3 p.m. Maximum charging current available from the panels is 50 amperes, and was found by dividing total Pmax of the panels by battery voltage. To fulfill this requirement, we need an MPPT charge controller for this system, having a maximum capacity of 60 amperes. But you need to limit the maximum charging current to 45 amperes here, since the battery pack is safe with maximum of 45 amperes charging current only. Since battery charging time is 6.6 hours, we can charge the battery pack fully in one day, if sunlight is available freely. Now you have hybrid inverters, where both charge controller and the inverter comes as one unit. We can replace these two with a hybrid inverter, and connect the solar panels and the battery pack as done before, and also connect the required AC equipment to the output terminals. Actually, hybrid inverter means that this inverter can charge the battery pack through solar panels as well as by AC power when grid power is available. Further, generator power also can be used in a situation where sunlight and grid power is not available. Now there are inverters with inbuilt battery chargers also. These don't have solar power connection, since battery charging is through AC power supply only. You will see here, in addition to the battery connection cables, there is a UPS power supply cable also, to connect the inverter to the AC power for battery charging. Here too, battery is connected to the inverter with supplied cables, and the power cable is to be connected to the AC grid supply. During the power cut, battery will start discharging through the inverter, to supply AC output power to the electrical equipment. When grid power is back, inbuilt charger will start charging the battery through the power cable connected to the grid. Hope you got fair idea now on how to design a solar off-grid system to be used during a power cut. If this video is helpful to you, please subscribe to the channel. Thank you.